Hi guys, I hope you're enjoying your snow day. So in these notes, we are going to talk about absolute extrema and the extreme value theorem. We've talked about relative extrema before with relative maxes and relative mins. Today we're going to talk about absolute extrema for the whole domain. Okay, so first of all, a review of relative extrema. We saw this last semester too. So with this graph, the y value f of a would be a relative max because it's greater than the points around it. You can see it kind of reaches that max and then starts coming back down. The y value f of b is going to be a relative minimum. It's not the lowest point on the whole graph, but it's the lowest point in its little neighborhood there. And then f of c is a relative max. We also have intervals of increase and decrease with this graph. It increases from the left of a, so from negative infinity to a. Then it decreases from a to b. It turns at b, it's a turning point. It starts increasing again until we get to c. And then at c, it is decreasing off to infinity. Okay, so relative extrema are what we've done in the past. And that's what we just looked at now. So relative extrema on an open interval for a max, if there's an open interval containing the x value c, such that f of c is greater than or equal to f of x for all x in that interval, then f of c is called a relative or local max. And vice versa, if f of c is less than f of x for everything in that interval, so kind of in that neighborhood, then it's a relative or local minimum of f. But what we're going to be dealing with now, what we're going to be looking at now are absolute extrema, which are for the entire domain. So the greatest max of all of them and the least min of all of them. And not every graph is going to have an absolute max and or an absolute min. It may have both, it may have neither, it may just have one or the other. It kind of depends on the behavior of that function family. So absolute extrema are for the entire domain. Okay, so the example on the left is what an absolute max would look like. And notice that both ends of that graph are decreasing without bound, because if one of them were increasing without bound, the graph would not have an absolute max. And then on the right side of the screen, you'll see an absolute minimum. Notice this is at a corner where the derivative would be undefined. But that's an, excuse me, I'm yawning. Absolute minimum. And notice also again with the end behavior of this graph that both ends are increasing without bound. So this comes back, like with relative extrema, to critical numbers. So extrema of any form, relative or absolute, can only exist either at an endpoint or at a critical number. So critical numbers are where f prime is either 0 or undefined. So 0 would be a horizontal tangent. I've got the little graph from the previous unit down there at the bottom to remind you of what those look like. So when you're at a turning point on the graph and the derivative is 0, you're going to have that horizontal tangent. Okay? Or corners and cusps, which are just curvy corners, also can give you maxes and mins. So we also have to look to see where f prime is undefined. Okay, so those two things combined, where f prime is either 0 or undefined, those are critical numbers. Okay, and those are what we need to check, along with the endpoints, when we have endpoints, to see where we might have absolute maxes and mins. So the formal definition, we looked at this a moment ago, is it's the absolute global max if it's the greatest y value of the whole domain. It's the absolute min if it's the least y value for the whole domain. So on this graph, the absolute minimum of this graph would be at f of b, that lowest point down there at the bottom of the graph. But because both ends of this graph are increasing without bound, there is no maximum on this graph. It increases forever. Okay, so this is a slightly different version of that same graph in that it now has endpoints. So now we've switched to graphing it on a closed interval from A to C. the x values. Now the absolute minimum hasn't moved. It's still at f of b. But now it's not increasing forever. It stops. It stops at f of c. So now that we have endpoints, notice that we have both an absolute minimum and an absolute max. So if you think about it, what that means is that if the graph stops on both ends, right, there's a left end and a right end, then somewhere between that left and right, one of those points has to be the greatest point. And there may be a few different that are the same y value, but one of those y values has to be the greatest. And one of those y values has to be the absolute least. But still, those absolute extrema have to be either at the critical number, like here at b, because at b the derivative would be 0, or they could be at the endpoints, like f of c here. So what the extreme value theorem says is kind of common sense. If f is continuous on a closed interval from a to b, then f has both an absolute minimum and an absolute max. So in other words, like we were saying a moment ago, if the graph stops from left to right, okay, one of those y values in that interval has to be greater than the others. And one of the y values also has to be less than everything else. In other words, something's a max and something's a min, so long as the space is closed in. Okay? If it goes off to infinity, this doesn't apply, obviously. It might not ever reach a maximum because it keeps going up, 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 or vice versa for a minimum. Okay? So what do we do with this theorem? Well, if you're trying to find an absolute max or min on a closed interval, you find the critical numbers. So this will be like what we did in the last unit with relative maxes and mins. We were trying to find those, and we used sign charts in the past for that. We're not going to use sign charts this time, though. We're actually going to look at the function values because we want to know, okay, that's great. We've got two maxes, but which one's bigger than the other, right? We want to know the absolute max. So we're still going to find those critical numbers by finding where the derivative f prime is either equal to 0 or undefined. And then what we're going to do is we're going to go back to the original function f and see at both the endpoints as well as at those critical numbers which of those outputs gives us the largest value and which gives us the least. Because we said those maxes and mins can only happen at critical numbers, so it has to be either those critical numbers or the endpoints. Whichever one is the biggest is your absolute max for the whole domain. It is guaranteed to be the largest possible value you can get out of that function on that interval. And likewise, the smallest of those y values you get out of f of x has to be the absolute least on that interval. Okay, so all of this comes with the caveat on that interval. Okay, obviously if we were looking at all real numbers, that would not necessarily be the case anymore. So the first step will be similar to what we've done in the past. We're going to find the critical numbers, but then we're going to take critical numbers and the endpoints and just start plugging them into the original function f to see what it gives us.